This is Geometry, Chapter 4, Section 4, in which we will be proving triangles are congruent using SSS and SAS. And those things stand for something, and you'll pick that up here in a few minutes. Last time when we talked about congruent triangles, we figured out, or we showed, that we needed to have all three sets of sides congruent and all three sets of angles congruent. Now that it would entail having 6 statements. Now the theory here is that we can get by with fewer than 6 if we know these special rules. And we're going to study the first 2 of them here in this video. We're going to talk about the SSS idea and the SAS. Our first one is postulate 4.1. Side, side, side. That's what the S's stand for. Side, side, side congruence. And the name tells you everything you really need to know. If you have all 3 of the sides in one triangle congruent to the matching sides of a second triangle, then you've got enough. Everything else will follow from it. So you can say then the 2 triangles are congruent. Notice now all we have to do is show 3 things are true instead of 6. So that simplifies things for us. It cuts our work in half. So we're going to have some real fun here. They're going to give us a triangle, JKL, that has vertices at these 3 points, 2, 5, 1, 1, and 5, 2. Then there's another triangle, NPQ, with vertices as given. And the question is, do we have congruent triangles? Well, the only weapon we have right now is we need to have congruent sets of sides. How do we find the lengths of the sides? Hopefully, I just heard you say, use the distance formula. So we're going to use the distance formula a bunch. Yes, I know. Get over it. Okay, you're going to have to work through it. There's just no way around it. So for JK, 2 minus 1 squared plus 5 minus 1 squared gives me 1 plus 16. 5 minus 1 is 4. 4 squared is 16. So we get the square root of 17. If you want to get a decimal, it's 4.123. But we don't necessarily need it for this, so I'm just going to stop at the square root of 17. KL, 1 minus 5 squared plus 1 minus 2 squared. Now here again, I'll caution you to use parentheses when you put this in your calculator, because 1 minus 5 is negative 4. Negative 4 squared is not negative 16, and in some of your calculators, if you're not careful, you'll get negative 16, and you'll get negative 1 here, so you would have a negative 17, and that's not good. You can't take the square root of a negative, so watch your parentheses here. Then we'll do side LJ, plug those numbers in and crunch through. 9 plus 9, so we have the square root of 18. So now we know the side lengths for the first triangle. We're hoping to get, if we're going to have congruency, we're hoping to get the same side lengths down here. Okay. Well, let's try NP. Plug that through, negative 3 minus negative 7. And then 0 minus 1, and square those. We get 16 plus 1, which is the square root of 17. This is looking promising. Okay. PQ Negative 7 minus negative 4 squared, 1 minus 4 squared. 9 plus 9, hey, we have a square root of 18. That matches. So now all we need is a square root of 17, and we're in business. So let's see if we get one. Negative 4 minus negative 3 squared and 4 minus 0 squared. 1 plus 16 gives us a square root of 17. So since we have 3 sets of congruent sides, we can say absolutely, yes, these triangles are in fact congruent. JKL is congruent to NPQ. Now another idea to talk about is this idea if you have 2 adjacent sides in a polygon, so 2 sides that are next to each other, they're going to form an angle. That angle that they form is called an included angle. Okay? It's included within the 2 sides. It's in between them. And that's an important idea to give us our second postulate. Postulate 4.2, side angle side, or SAS. If you have 2 sides and you have the angle between them, the included angle, in one triangle, congruent to 2 sides and the included angle between those in a second triangle, that should even be singular, then the triangles themselves are congruent. Again, notice we only need 3 things. We need 2 sets of sides and 1 set of angles. So we only need 3 of the 6 possibilities to make life good. And this is called side angle side. So our job here, we're going to write a paragraph proof, because we haven't practiced one of those lately. So we're going to do one. And they've given us this beautiful picture with some triangles all over the place. And we're trying to prove some angles are congruent. I want to prove that angle CFD is the same as angle CEB. Well, we'll start with the given information. We're given that these things are all true. Now, I'm going to say that I can use the SAS postulate. You could put the number if you wanted to, postulate 4.2, but typically people just use what they're called, SAS in this case. Since I know SAS is true, I've got everything I need to say this triangle BCF, okay, BCF is congruent to DCE. Okay, I've got a side BC matching DC. I've got CF matching CE. And then I've got the included angles are equal. So I've got enough to say this left-hand triangle is congruent to the right-hand triangle. So since I know the triangles are congruent, I can say that this angle BFC is congruent to this angle DEC. Now that's almost what I want. Remember, I'm looking for the angle inside this middle triangle. I'm looking for those 2 angles. Well, I've got the ones next to them. Oops. I did not move my angles over here. Shame, shame. Now, since I know BFC and EFC form, what do those two make? BFC and EFC. They make a linear pair. And so do DEC and FEC. Those are both linear pairs, which means they're both supplementary angles. So then I can say that the angles I want, CFD and CEB, are congruent because of the congruent supplements theorem. I could do a whole lot of substitution if I wanted to, but I didn't want to. I didn't want to go work that hard. So I've gotten where I wanted to go using congruent triangles. Now, I made this statement here, or my reason actually, since the triangles are congruent. I'm using the definition of congruent triangles there. You will run into some books, and sometimes I'll even say it myself. There's an abbreviation here that a lot of books use to talk about congruent triangles. CPCTC. Corresponding parts of congruent triangles are congruent. If you know you have congruent triangles, you can use CPCTC as a reason for why something else is true. So instead of saying since the triangles are congruent, I could have said because CPCTC, we can say blah, blah, blah. Okay? Don't get too tangled up in this. I just wanted you to see it so that you're exposed to it, and if you see it and hear it again later, you've at least had an idea of what it means. It's also kind of fun to say, CPCTC. It's a nice little tongue twister to work on. As always, now that we've gone through our SSS and SAS postulates, if you had questions along the way, I hope you wrote those down. Bring them in with you, and we'll see you in class.